Hello everyone and welcome back to another video. Today we'll be taking a look into our chess engine in a bit more detail. So in the past couple of videos, we've covered the foundation functions, the UI side of things, the legal moves and the evaluation. And in the very last video, we looked at the best move function. Okay, so just to recap, the best move function basically just determines what the best moves are from a certain position. Like, it gives a static evaluation of the position, and then it returns an array of all the best moves. Okay, so now we'll be taking we'll be building upon what we did in the previous video with the decide move function. So basically, as we discussed last time, the limitation of the best move function was basically that it only takes the static evaluation of a certain position. But the decide move function will basically bear in mind what the opponent will respond with, and then it will base its evaluation on what the opponent will respond with. So this basically allows it to look a few moves into the future, which basically makes for a more developed and well-rounded chess engine. So this is a very important function. And now let's just have a quick look at exactly how this works in code. Okay, so first of all, we have a handful of different things which we take as parameters over here. Also, I should mention this is on line 649 in case you would like to follow along on GitHub. First of all, we take in several different parameters. So this alpha and beta, basically just forget about that for now. I'll explain this like in about 10 minutes when I come into like how we optimize this decide move function. But then basically one thing which is very important is we decide to move for a particular color. So it would basically be different for if black were to move or white to move, obviously. And then we also have the depth. So this depth is basically the number of moves we look ahead. So let's say in chess traditionally, a depth of 1 is associated with looking one move for black and one move for white. But then when creating chess engines, like in the world of chess engines, we consider half depths, if you like. So this basically means each move is one half depth. So for example, depth 2 would be 4 moves, but then that would be 4 half moves. So which is the depth we'll be using here. And then we obviously take the current board and current pieces as parameter as well. And now the first thing which we do is we basically need to generate all possible moves. And then we need to how this function works is it's basically recursive, since the best move for a certain position will be whatever the, out of all the moves in the next position, whichever one of them is the best move. And now for each of them, it will be whichever ones in the future moves are the best move. So it's basically recursive, which is why we basically have our base case. Our base case is here. I'll go through this a bit later because it won't really make sense now, but we can go through this a bit later, no worries. So pretty much, this is the main heart of the code. This basically just determines for each of the selected best moves. So the selected best move is basically, remember, the static evaluation of this certain position, which we get from the best move function, as we discussed in the previous video. All of these are the selected best moves. So this is basically like a best guess, if you like, of what the chess engine thinks are going to be the best moves, and then evaluates these in order, okay? So for each of these selected best moves, we take the squares of both of them, and now first of all, if it's empty, then we basically just break, since we basically reach the end of the selected best moves. But then also, what we do is we need to play this move, like we need to basically carry this move out on a certain board, and then update the new pieces and new board respectively. So, and then after we do that, we basically set these, send these new variables, new pieces and new board, over to the decide move, and then except this decide move will be for the opposite color, so 1 minus color, and then it will be for a depth which is 1 lower than the current depth, so it will be depth minus 1. And now the reason why we have this positions minus 2 is because let's say on the first move you're analyzing 20 different positions. There's no point analyzing 20 different positions for each of the subsequent moves, right? Since, for example, if we still analyze 20 different positions on like the 7th move, then the probability of the probability of one of those 20 moves actually being relevant is very low, right? Since it's only the first move where we need to look at as many positions as possible, and then after that move we can basically start like narrowing down our search just so we can increase our depth, right? Since it's basically a game between like how deep do we want it to go and how much breadth we want it to cover. since ideally in an ideal world we would go to maximum depth and maximum breadth as well. All possible moves for all possible moves in the future as well. However, we obviously have resource limitations of like the actual computer, so which is why we need to do such like optimizations just to reduce the number of positions which we look at, since most likely a few moves later on looking at as many positions won't be as good. So which is why we have this certain positions -2. And then after we do that is we basically just set the selected best move, we set that particular array element to equaling evaluation, so the current evaluation of this particular position. And now over here is basically the alpha beta pruning. So I'll go over that in literally just 1 second, but it's basically just an optimization. Like you can consider it to be a way in which we can increase the speed and memory consumption of the program. And now after we repeat this for each of the selected best moves, so for each of the selected best moves, we basically just sort that in order of the evaluation. And now what we do is we basically sort them reversed if the color is white. So this basically means that we sort it in descending order if the color is white. So we'll be starting from the maximum evaluation, i.e. the best one for white. But then if the color is black, then it basically means reverse is false. That means we'll be sorting it in descending order. So that basically means that we'll have the most negative ones first. So we'll be sorting in ascending order, not descending order. So we'll have like the most negative functions, which are the best ones for black first. And then after we do all this, we basically just return whatever the selected best moves 0, selected best moves 0, 0, 0, 1. So this 0 is basically the first element of the selected best moves. And then this 0 and this 0 is the starting coordinate, and this 1 is the ending coordinate. And we send this as a tuple since these are the coordinates. And then after that, we send the evaluation of whatever that position is. We send all of this to the play function. Now, the play function is also a mammoth function. We'll be taking a look at that in the next video. But then, and now, after we basically carry this out, we basically, since this is a recursive function, so over here we go on to depth -1. So let's say we start with depth 4 and color black. Then we go to depth 3, color white, and then we go back to depth 2, color black, etc., etc. But then eventually we'll reach depth 0. So after we reach depth 0, we can't continue. So what we basically do is we basically just perform a static evaluation. So this static evaluation is just going to leverage the best move function. And then this basically just takes the first couple of best static evaluation positions, and then it returns whatever that whatever the top position is within the static evaluations. Okay, so that's pretty much it for this decide move. And now we have the optimizations. So this optimization is basically alpha beta. So alpha beta pruning is a huge topic. Like I won't explain it in this video. Feel free to watch like a video on it like on YouTube. There are plenty of good ones, which is how I learned it myself in the first place. But like after you've looked at that, you can look at how exactly we use the alpha beta pruning in our code. So I assume you're already familiar with that. If not, just feel free to watch a video. Alpha beta pruning is essentially a way in which we can restrict the number of ways in which we can, in the number of positions which we have to look at. So we basically do this by, like if the color is 0, i.e. it's black, then we basically know that if beta is less than or equal to alpha, so this basically means that if the position is worse for white, i.e. better for black, than alpha, then we basically need to break. Now the reason why we need to do this, remember, is because black, we know that the color above it, which will be white in this case, since we're currently looking at black in this branch, so the color above this branch will be white. Since we know that white will never enter this branch, since white already has a better alternative in a different branch. So which is where this, and the reason why we set beta to equaling the minimum of the beta in the current evaluation is because we want whatever the least valued evaluation is in this current position. And then otherwise, if the color is 1, then we basically take alpha, and then we set alpha to equaling the max of alpha in the current evaluation. And then we do the exact same thing. If beta is less than or equal to alpha, then we break. And now we basically do this for all of these values, for all of these selected best moves, and we constantly update this. And now ideally, if our selected best students are basically sorted in order of how good they are, then we'll basically be able to maximally use this like alpha beta pruning, and then therefore our algorithm will be like the maximal efficient. So which is why it's essential that our best move is as accurate as possible, and the best move in turn just relies on the evaluation function. So in turn, basically how good our evaluation function directly impacts everything else inside our code. Okay, so that's pretty much it for this particular video covering the design move. I really hope you enjoyed watching. Hopefully you learned something new. Hopefully you learned a lot of things new actually for this particular video. It was quite a complicated one, but if you stuck with it, I congratulate you. Like you've certainly like accomplished a lot. And if you enjoyed this video, please be sure to leave a like and subscribe. It would be very much appreciated. And I hope to see you in another video next time. Thanks for watching. Bye.